Поехали. Спасибо, да. Спасибо большое. Угу. Сейчас, где? Изнутри? И с другой стороны? Вот. Ага. Так чего, начинать? Спасибо. So let's start. First, an important comment about the Ostrovsky theorem. And what's your name? Vlad. Очень приятно. So I disregarded, forgot about it last time, but Vlad kindly reminded me. So Ostrovsky theorem was classification of norms on the field of rational numbers, and Q is a global field, so-called global field. And then if you take some norm and complete, you get a completion like this that is called a local field. And why? Because there is this famous numbers versus functions analogy, and then the functional analogy of this will be the field of rational functions on some curve. So X, a curve over the finite field FQ. Well, say the simplest possible case is just FQ of, say, P1 or A1, it doesn't matter. So it's just the field of rational functions, like this. And then the problem is the similar analogous problem will be to find all the possible norms on this field. And then the answer is you fix a point. So classification of non-trivial norms. On this global field, F equals say T. So it says that they are all non-Archimedean. And they are given just by the points small x in P1. Now there is a certain maybe psychological problem about this, because we are used to geometry over say complex numbers, and complex numbers form an algebraically closed field. But here the finite field is drastically different. It's definitely not algebraically closed. So maybe first let's consider some, well, sort of aside. We can consider the field of rational functions of one variable over T. Again, rational functions over the projective line, but now projective line is over complex numbers. And here, all the norms are like we fix some point A or maybe again x in P1, and the norm will be denoted sub x of some function f. Okay, and then this norm will be again say e, because there is no preferred prime number in this case. So let me take e, for example, as a base of my exponent. E to the power negative valuation of f at point x. And what is the, or again, there is a synonym, e to the power negative order at x of our function f. And what is this order? Is the order of vanishing or pole. Say order of t minus x is 1. Okay, and order of t over t minus x squared is negative 2. Okay, so it depends on the local behavior of this function around this point. Okay, and then the completion of our global field with respect to this norm will be always isomorphic to the field of formal Laurent series, well, of some variable, maybe let me call it z, where z is a local parameter at x. So if x is a finite point, then z is t minus x. And if x is infinity, the infinite point in P1, then z is what? What is the local parameter at infinity? Pardon me? Yes? Right, TT inverse, absolutely, yes. Thank you. Fine, so, pardon me? Yeah, well, maybe let me denote it this way. Completion, yeah. So it's not algebraic closure, but completion, yeah. With respect to this norm. So all the completions are isomorphic. It is again drastically different from our last time when all the completions were different. In this case, all the completions are the same. They are all absolutely isomorphic to the same formal Laurent series field. Fine. Now, maybe just one quick survey. When we are at infinity, what is the explicit description of the order at infinity? So we have, for example, a polynomial. P of t. And I ask you what order at infinity of this polynomial. What is it? Pardon me? Right. It's just the degree of p. Okay. So the usual degree of polynomial always gives rise to some non-Archimedean evaluation and norm. Fine. Now back to our original problem with a non-algebraically closed field FQ. Then the points of P1 over FQ, so to say, are infinity again. Then the same will be true. The evaluation will be just the degree of polynomial, and finite points of A1 of FQ, so to say. or maybe I should write this. If I write it in the brackets to the right, then it usually means just the points, and there are finitely many such points, and this is not what I mean. And here, when I classify the points of the affine line, they are the same as maximal ideals of the ring of functions. And this is the same as pardon me? Maximal? No, why homogeneous? Just maximal ideals of this ring. So the same as irreducible monic polynomials of degree, well, of positive degree. And well, for example, if the polynomials are of degree 1, then they are given just by the numbers in the ground field. Okay, but if degree is 2, for example, then they are rather given by numbers in the quadratic extension. It's unique for finite field, but up to automorphism, sort of conjugation, Frobenius automorphism. So in other words, I can say that these are Frobenius orbits in this similar thing in A1 FQ bar. That's just FQ bar. So for example, if again driving the same analogy, we would consider the real line. Yeah, then the points in this sense of the real line would be the points of the complex line up to complex conjugation. Okay, so there will be all the real points. These are irreducible polynomials of degree 1, but we also have irreducible polynomials of degree 2. And they have 2 conjugate complex roots. So these are the points in this sense. In other words, there's just the upper half plane. Okay, so this is the classification of points or valuations of the field of rational functions in one variable. But more generally, if you have some curve, you will have points of this curve, but in the same sense, say elliptic curve or whatever. So there will be infinitely many points, not only the ones defined over the finite field, but all the points defined over the algebraic closure modulo the action of Frobenius. This will be the classification. And now you see, I hope, why this etymology, why some fields are called global and some fields are called local. Because the local fields, yeah, maybe I should also say that the completion say fq of t with respect to the norm at point x will be absolutely isomorphic to some field of formal Laurent series, but the ground field will be extended. It will be some q prime. And now q prime is q to the power degree of x. Well, again, x is an irreducible polynomial. It has some degree. And here is this degree. Yes. What happens if x is two-dimensional? Well, then there are many more valuations. For example, all the divisors, all the reducible divisors give rise to valuations, but not only. You can also take any blow up and any reducible divisor on any blow up. It will also give rise to valuation. Well, it's an interesting branch of science, but too far of our mainstream. Pardon me? Yeah, for example, okay, so you see that any completion will look like this, and it will somehow be responsible for local behavior of our rational functions around some point. And for this reason, those fields are called local fields. Well, in contrast, the original field is called global, because it's about global curve. And local field is about behavior at just one point. So the deliberation of functions here is global, but if you're only interested in behavior around this point, you will get the local field of Laurent series. Pardon me? Yes. Yes. It's a restricted product topology, yeah. So the basic, or how's it called? The base of open sets consists of infinite products of open sets, but almost all of them must be the standard ZP. Okay? Yes. No, the local field is the completion, but it has inside it has some ring of integers, the formal Taylor series. And this is the maximal ideal T times FQ prime. The quotient by model ideal will model of the ideal will be this finite extension FQ prime, if that's what you ask. The local field, once again, is this, but it has a field of residues. The field of residues is FQ prime. Okay, so well, I hope I answered Vlad's suggestion. Yeah, or anything else? Fine, thanks. And now, as you see, our local fields have one drastic difference compared to the Archimedean case, namely that in the Archimedean case, the local field was R, or complex numbers, and it was almost algebraically closed. Complex numbers are just algebraically closed. R is almost closed. You just add imaginary unit and you get complex numbers. But this is very far from what happens in p-adic case. The field of p-adic numbers is not algebraically closed at all. There are equations of arbitrary degree that have no roots. And the same happens in this geometric situation. So, well, our next big goal is to construct a sort of p-adic analog of complex numbers. So a field that is p-adic, non-Archimedean, but is algebraically closed, and also complete. And complete. And it's called Tate field, since it was first constructed by John Tate. And it will be done in 2 steps. So we start with QP. It is complete, but not algebraically closed. So then we will pass to its algebraic closure. And then it will inherit some norm and topology. but it will be not complete. So then we'll pass to its completion. And this already will be complete and algebraically closed, and this will be the Tate field CP. Okay, and then we'll see why it is useful. Okay, but first, just it will take us quite a few classes, maybe 3 classes, to do this. But first, let's discuss what happens in the geometric situation. So, say if we start, yes. Yes. We will. Well, we'll discuss this in October. Huh? Absolutely, no. Okay, so let's consider the local field like this, and take its algebraic closure. So does anybody know what we get? Yeah. It's called Puiseux series. Though I have trouble. I guess it's like this. Yeah, but maybe I'm wrong. A Puiseux series, and what does it mean? So a typical Puiseux series, F, looks like some formal series. Say I, or maybe n is greater than negative n to infinity, and then I take an t to the power n, and this is a usual Laurent series, but now I allow roots of t. So I write like this for some fixed k. Okay, but for other Puiseux series, this k can be something else. But for one particular series, there is a common denominator. Okay, so you cannot take t to 1/2 plus t to 1/3 to 1/4, and so on. This is not allowed. Your denominator must be fixed, whatever it is. Yeah, for example, yeah, because any 2 rational numbers have a common denominator, right? Yeah, so there is no problem. Pardon me? K is an integer, yeah. Okay, so in fact, we will discuss this maybe in a month in more detail, but that's the answer. And yes? Pardon me? Yes, I add all the roots of t, yes, if that's what you ask. So I take the basic field, and then I add the elements t 1/2, t1 third, fourth, and so on. So I add the roots of unity of any degree. Okay, and root of unity, but of the parameter t. And that's the answer. Unfortunately, in this, for example, if we move to the case fq of t, then certainly it's not true for one stupid reason. So what else do I have to add? Yeah, for example, you certainly need to take algebraic closure of the field of constants. Okay, so first you must have this. Then you may take also a Puiseux series, and still it won't be enough. Okay, so you will need more things to add. We'll discuss this in October, but it's harder. And the same difficulty happens in p-adic field. So, well, here you take so-called non-ramified extensions that only come from extending the residue field. Then you can add some roots of the uniformizer, say p, but it's not enough. You still need more. Okay, so this will be our program for the next month. And today we will study just some particular extension. Well, nothing very particular, but just one fixed extension. So I have QP, and you will have some finite extension K. Okay. In fact, when people say a local field, they always mean either finite extensions of QP or of the geometric local field of Lorentz series over finite field. Okay, but these are all of the same sort. All the finite extensions of the local field characteristic P looks like this for different Q. Okay, so the extension itself may be very non-trivial, but abstractly, as a field without a subfield, it looks just like this. Okay, so in a sense, there are smaller number of local fields of finite characteristic than characteristic zero. Okay, and yes. FQ itself, no, it's a finite field. It's nothing. Yeah, it's previous level of difficulty. So it's zero level field. The level 1 are local fields, and so to say level 2 are global fields. So, well, somehow historically, local fields are just technical instruments for the study of global fields. So we're interested in arithmetic of rational numbers, and to study it, we just use all the completions. Fine. So our first goal, goal for today, will be to prove an important theorem that our usual p-adic norm on QP admits a unique extension to this field K. So there is a unique norm on K whose restriction to subfield QP is the standard norm like this. So it exists and it is unique. The fact that it's unique is very simple, and we will prove this first. Uniqueness. And to prove this, we need only some very rough structure of K, namely as a finite dimensional vector space over QP. Well, maybe let me call this space V. So we don't need multiplication, just addition and multiplication by scalars. Okay, and well, we define a norm on V from V to say real numbers. Sorry, but non-negative real numbers. And what do we need from this? First of all, that the norm of some scalar lambda times v is our usual p-adic norm of lambda times the norm of v. Okay, then the norm of v equals 0 if and only if v is 0. And then certainly we need the usual triangle inequality, that the norm of v plus u is less than or equal to the norm of v plus the norm of u. Okay, and then the lemma we are going to prove is that any two norms on V are equivalent. And what does it mean? It is somehow different from the notion of equivalence on the base field. Last time we had some exponential inequalities, but here the inequalities are very simple. So we have one norm, one of V, say for some constant C, is less than or equal to the norm number 2, less than or equal to constant V, like this. So it's true for any V, and there are some constants such that this holds for any V. Okay, so once again, they define the same topology. The balls in one norm contain the balls in the other norm and are contained in the balls in the other norm. Okay, and the lemma claims that any two norms are equivalent. And to prove this, we introduce one particular norm. Do you have any suggestions? Yeah, the supremum norm, right? And then we prove that any other norm is equivalent to this one. So we choose a basis. Say V1 and so on, Vn in our vector space. And so any vector V is a linear combination of these guys. And then this supremum norm is defined as the maximal p-adic norm of coefficients. Okay, so then it's clear that all these properties are satisfied. It's a norm, and now let's see how is it related to some other norm. Well, we know that some other norm V is less than or equal, well, yeah, is less than or equal to the norm of A1 V1 plus so on plus norm of AR and Vn. Okay, and then this is equal to the usual p-adic norm of A1 times norm of V1 plus so on plus the usual p-adic norm of An times the norm of Vn. Okay, and how can we estimate this? Yes, yes. So this at most the sup norm times maybe n times the maximal of norm of V1, so on, the norm of Vn. Okay, so anyway, this is some constant. So we do have an estimate like this in one direction. We need an estimate in the opposite direction. So in the opposite estimate. And to this end, we consider, well, it's enough to consider the unit sphere, because these constants, C small and capital, are just the values of other norm on the unit sphere of this norm, or maybe inverse. So take S in the unit sphere of the supremum norm. And then I claim that the other norm is bigger than some epsilon, that is bigger than 0, on the unit sphere. And this is just what we need. So this other norm cannot go infinitely close to 0. Yeah? So let's prove this just by reduction to absurd. So assume otherwise. We have vectors V, sorry, maybe let's call it U. U1, U2, pardon me? But it can be 0, yeah, well, you're yeah, well, right. So what you say is true, and I plan just to repeat your words. So, but you know, if it's clear to everybody, then I'm happy and we go on. So should I repeat Petya's words, or is it clear? Huh? Please do, or what? Okay. So there is some sequence, and their norm goes to 0. Sorry, supremum norm is 1, but this norm goes to 0. And now the unit sphere in the supremum norm is compact. So it's closed and bounded and is compact. So it means this infinite sequence, U1, U2, and so on, has a subsequence that converges to a point on this sphere. And then, if it's clear to everybody how this argument goes, just tell me, or maybe let's take a vote, when I say converges, what do I mean? In which topology? Supremum norm or V norm? So what's your opinion? U prime 1, so on. U prime 2, so on. That converges to some point U in the sphere. Now, in which topology? Who votes for V topology? Who votes for supremum topology? Okay, the absolute majority. Right, in supremum topology. Okay, and then we know that the norm of U, but in V topology, is 0. And why this is so? Because it is not more than the norm of U minus UR prime. In which topology? Pardon me? Right. So it doesn't matter much, right? But still, let's do one thing accurately. So I need this, right? And now what do I say? So this is small by assumption for big R. And for this, we only know that it's bounded by the supremum norm, and this is also small. It's also small. Okay? So in other words, this thing is small and goes to 0. And hence, U V is 0, sorry. And hence U is 0, but that's a contradiction because 0 is not in the unit sphere. Okay, yes? But what if, yes. So I assumed that the V norm is not bounded from below. Yeah, then I can take an element of V norm 1/2, 1/4, 1/8, and so on, that goes to 0. Okay, now of this sequence, I can take a subsequence that converges in the supremum topology, right? Because the sphere is compact in supremum topology. Then I take this limit, and this limit must be 0, which is nonsense, right? Okay, so we proved this. So there is some epsilon like this, and then I conclude that the norm, the supremum norm is less than or equal to epsilon inverse V norm on the unit sphere, and everywhere by renormalizing, because if I have any vector at all, say U, then I replace U by U time of A max inverse U. Okay, so I write U as the sum of AI VI. Then I take the element of the maximal norm, and then this lies in the unit sphere. But since I just divide by some scalar, it divides both norms by the norm of this scalar. Okay, so this is proved. We know that any two norms on a finite dimensional vector space are equivalent. And let's proceed to the field. If you remember, our initial goal was to prove the uniqueness of norm extension from p-adic to field. Okay. So we take some norm extension and maybe some other norm extension to the field K, and we want to compare them. So we take, well, back to uniqueness of norm extension from QP to K. So we have two norms, and we know that one norm is bounded by the other norm. Okay, there is some universal constant C just by what we proved. It's a finite dimensional case, finite dimensional vector space over QP. And we want to prove that, in fact, they are equal. Otherwise, so if the norms are not equal, then there is some C, well, some maybe D, 1 less than D less than or equal to C, such that, and also, so this is for any x, and some x in K, such that the norm of x, the first norm, is exactly D times the second norm of x. Okay? And no. So either they are absolutely equal, or sometimes they're not equal, and there is some ratio, okay, which I can assume is bigger than 1. Well, say, or else if the C is less than 1, then I can reverse the roles. So it doesn't matter. Well, just for the sake of definiteness, let's assume that C is bigger than 1, that D is bigger than 1. The same bad thing will happen if it's less than 1. So now, as p-adic suggests, just take some big power. So the norm of x to the power n will be d to the power n, x to the power n norm here, but d to the power n will be bigger than c for big enough n. Okay, this will be a contradiction to our assumption. Okay, so the uniqueness is done. And now about existence. For existence, we just give an explicit formula so it's a degree n extension. Or some n. And I have a multiplicative homomorphism from the multiplicative group of K to the multiplicative group of QP called norm. And does anybody not know what is the norm? So everybody knows what is norm, or the usual norm in the field extensions. Everybody knows what is norm. I shouldn't recall this. One of the many equivalent definitions. Okay. So again, we degrade. We view K is a vector space over QP, and then any element alpha in K gives rise to a linear operator, just multiplication by alpha. Say A sub alpha from V to itself, namely gamma goes to gamma alpha, just multiplication operator. And then this norm of alpha, by definition, is the determinant of this operator. Okay? And for example, if alpha lies in the ground field QP, then the norm of alpha is what? Yes, alpha to the power n, because it's just the scalar operator. Fine. And so the formula for the extension of this norm is the usual p-adic norm of the norm, say, x. So that's a good try, but wrong, because it's inconsistent with the ground field norm. So I have to take to the power 1 over n. And then it's fine. This is the correct formula. Pardon me? Yes? Yeah, so it will be related to the valuation with respect to this maximal ideal. Absolutely, yes. This will be, and it is unique. Well, uniqueness we already proved. It will work, but somehow logically we start with this, and then we'll derive what you say. So whatever you say is true always, but we'll take some other route to this. So what do I erase? Well, what do I have to check? Well, the only thing to check is what? Is the triangle inequality non-Archimedean type? That is the norm of alpha plus beta is less than or equal to the maximum of the norm of alpha and norm of beta. Okay, again we can renormalize. So say beta is this maximum, and then we set gamma is alpha over beta. Yes. Say it again. What? What is strange? Mm-hmm. Yes. This is sort of stronger. If we prove this, we're on the safe side. Yeah. Okay. So the norm of gamma is less than or equal to 1, and we have to prove, check, that the norm of 1 plus gamma is also less than or equal, well, less than or equal to 1. Okay, so this is our task for today, and it's not evident. Let's do this. So the first case, let's assume that gamma is primitive. That is, the whole field K is obtained by adding just this element gamma to QP. And then it's known in the standard Galois theory that since we're in characteristic 0, then such a gamma always exists. But we don't need to choose one. We are given one gamma from a start, and just we replace, if you wish, we replace our field K by the subfield generated by gamma. Okay. And then 1, gamma, and so on, gamma to the power n minus 1, form a base of this vector space over UP. And we say A is the matrix of duplication by gamma in this base. By the way, do you know how this matrix is called? It's very, very special, yeah, because 1 goes to gamma, gamma goes to gamma squared, and then this one goes to the whole Frobenius companion form, right? Okay. But we'll never use it. So now the norm of gamma, by definition, is the p-adic norm of determinant of A to the power 1 over n. Okay, so we will use the supremum norm on the vector space of matrices. With respect to the basis of elementary matrices. Matrix units. And we will argue sort of similarly. We will assume otherwise, and then we will produce a vector in the kernel of A, which is impossible. So A is invertible. So the claim is that the supremum norms of all the powers of A are bounded. so whatever powers we take, the matrix elements always stay bounded. So otherwise, we can take a subsequence. Sequence I sub j such that the norm of a to the power I sub j, well, let's call this bj, but it grows, so it's bigger than j. That's what we assume, that it grows linearly, so to say. So set beta j the maximal, well, maybe not z, but a maximal matrix element of a to the power ij, and so then bj is the p-adic norm of beta j. And now we renormalize and go to the unit sphere. Ij over beta j is, say, bj. So it lies in the unit sphere. And a subsequence of bj converges to some matrix B in the unit sphere. And now the determinant of bj is the determinant of aij times beta j to negative n. Yeah, just because we multiplied by the scalar matrix, which has determined beta j to negative n, and hence the determinant, the p-adic norm is less than the determinant of a to the power ij times j to negative n, because we assumed that there is this linear growth, or at least linear growth. So this is equal to the norm of gamma times n ij, j to negative n, but norm of gamma was less than 1, so it's less than j to negative n, and so this converges to 0. Okay, so we conclude that the determinant of B, the limit of our subsequence, must be 0. Okay, because the converging bj's have determinants that go to 0. Fine, the determinant of B is 0. So there is some non-zero element in our field such that bx is 0. The kernel is non-trivial. Okay, now from this we will derive that B itself is 0. So everything lies in its kernel. And this will be a nonsense because B was in the unit sphere. So why is B itself 0? just because B is the limit of the sequence up to normalization is the powers of matrix A. A was the matrix of multiplication by gamma. Okay, and gamma commutes with itself and with its powers. So it commutes with all those BJs. So it commutes with the limit B. But gamma generates everything. So you just take x, gamma squared x, and so on, and they all vanish. They all vanish. They're all killed by B. So gamma commutes with B J's, hence in the limit gamma commutes with B, hence yes. Which one? This one? Because we assume that the norm of gamma is less than 1 over there. So gamma commutes with B. So, for example, B gamma x is gamma bx is 0, and B gamma squared x is 0, and so on. But x, gamma x, and so on, gamma n minus 1 x form a base span the whole of K. Hence, B is absolute 0, and there's a contradiction because B was in the unit sphere. Okay, so we proved this claim that the supremum norm of powers of A is bounded. Fine. This is proved. Why do we need this? So we know that there is some constant C such that the norms of all powers of A are bounded above by C. And now the p-adic norm of determinant of A is certainly at most the maximum of the p-adic norms of matrix coefficients, maybe to the power n. Yeah, just because we write down the n factorial sum formula for determinant and apply the non-Archimedean triangle inequality. Okay, so this is the norm of A supremum to the power n. Okay, and now we are almost done because let's compute the norm of 1 plus gamma to the power capital N. This is the norm of determinant of 1 plus A to the power N, the power 1 over N, by definition. Yeah, that's just definition of our norm. And we know that this is at most norm of 1 plus A to the power N in supremum norm. Okay, and now we just use the Newton binomial formula. So there's at most maximum from I0 to capital N, the norm of n choose I, a to the power I, supremum norm. Again, we use the non-Archimedean inequality, so we get the maximum over all summons, because these are integers, yeah, and they have norm less than 1. And this we know, this is at most C. Okay, so we conclude that the norm of 1 plus gamma is less than or equal to C to the power 1 over n. And now, as n goes to infinity, we conclude that the norm of 1 plus gamma is less than or equal to 1. And that's a great success. This is what we wanted to prove. Great. But this was only under the additional assumption that our field K was generated by gamma. That gamma was a primitive element. And this is not necessarily true. But then it's no big problem. We just take a subfield K prime that is generated by gamma, and we compute just the formula for this norm in 2 steps. First, so if I have 2 fields K inside K prime, inside QP, then we can take any element alpha and take its norm from K to maybe from K to QP in 2 steps. We first compute its norm from K to K prime, and then compute the norm of this from K prime to QP. Okay, and this is clear, I hope. Yeah. So what do we say? We said K prime is the field generated by gamma, subfield generated by gamma, and then we know that 1 is bigger than the norm from K prime to QP of 1 plus gamma. This we have just proved to the power 1 over degree of K prime over QP. This we just proved, right? But this is nothing but the norm from K to QP of 1 plus gamma to the power 1 over n. And this is by definition the norm of 1 plus gamma. I mean, I use that when I take this norm. It is just taking to the degree. So in this case, my alpha, which is gamma, already lies in K prime. So when I take this norm, it just raises it to the power of this degree. Yeah. Gamma to the degree of k over k prime. Okay, so we are done with this. And now we have to make contact with what Piotr suggested, but I'm not sure. Well, at least let me formulate the claim. Maybe we'll prove it next time. Yes, that's what I mean exactly. And what will happen in 5 minutes? I mean, the recording will stop automatically. I see. So let's say it's proposition. So again, we have an extension of degree n, and we set A is the set of field elements with norm less than or equal to 1. And inside we take the subset M, which consists of the field elements whose norm is strictly less than 1. So then I claim that A is the integral closure of ZP in K. M is the unique maximal ideal in A, and the residue field F, that is just by definition A modulo this maximal ideal, is some finite field Fq, and here Q is some power of P, and F is at most n. So this power is not more than that degree. The degree of induced extension of the residue field is not more than the degree of this extension. Okay, so we'll prove this next time. That's very easy compared to what we just did, but still requires some time, more than 1 minute. Okay, so thank you for today. If anyone wants to submit his home assignment, everybody is very welcome.